This lecture is about Gauss's law being used to calculate electric fields. Last lecture we learnt about Coulomb's law, describing the force between two point charges, and we saw the rules about electric fields. This lecture we make it a little bit more complicated. We look at adding electric fields from a number of objects and finding the field from distributed charges, not just point charges. It will involve using integrals, but it will all be done for you, so don't worry about the equations you're going to see. Just sit back and relax, and I'll put some soothing music on in the background. If we have two charged objects, then they will both produce an electric field, and so we have to add the electric fields together. You can see here the field at a point P near a dipole, which is what we call two opposite charges near each other. The total field will be E1, which is the field due to Q1, plus E2, which is the field due to Q2, and they have to be added as vectors. Now let's look at what happens if we have a volume of charge. Just think of an electrically charged cloud of no particular shape. This cloud of charge is being sliced up into small blocks of charge. We're interested in the total field at a point P. Now each little block in the cloud has its own charge, and we label them delta Q1, delta Q2, delta Q3, etc. Each block produces a little bit of electric field that we call delta E. And so that field will depend on the charge, and it will also depend on the distance, R1, 2 and 3, from that particular block to P. So we can find the electric field from each block and add them as vectors. If we made the blocks really big, that wouldn't be a very accurate way of doing it. But if the blocks become smaller and smaller, it becomes a better and better representation of that cloud of charge. This method of dividing up and adding can be used in 3D volumes or on flat surfaces, and it's what we call the method of integration. Here, the area under that curve that you can see is being approximated by putting blocks under the curve. The area would then be found by adding the areas of the blocks. You'll notice that the thinner the blocks are, the more accurate the approximation. An integral is basically the limit of this process as the blocks become extremely thin. Now, before we go further, we need to define some measures of charge. Because we are talking about distributed charge, we need some different symbols. We know that Q is the charge at one point, which is no dimensions. But if the charge is distributed along a line that is in one dimension, we have to talk about the linear charge density that we call lambda, which is measured in coulombs per meter. For 2D planes, we have surface charge density, sigma, which is measured in coulombs per meter squared. And for volumes, we have the volume charge density, rho, measured in coulombs per cubic meter.